I'm going to give a quick overview of this project, and I'm going to start with what Caltrans wanted from this project, which was really for development of guidelines for the efficient design of reinforced concrete bridge columns, and specifically Slender bridge columns. The two approaches that are used these days for Slender columns is the approximate method, which uses moment magnifiers, but then there's also refined analysis, and as we saw in the previous presentation, oftentimes there's not much guidance on specifically what that means. The moment magnifying approach in AASHTO was developed from building codes, namely ACI building code 318. And some of the analogies are going to carry over to bridges, some won't. Engineers have made conservative assumptions to fill in the gaps, but also the ACI provisions have some conservatism built in as well that might not make sense these days, and there's better approaches that could be had. So Professor Scott and I wrote a proposal, and it was accepted, and what we were looking at was really an analytical approach to solving this problem. There's lots of experimental results on Slender beam columns, and we're going to leverage those within the context of analyses to develop the guidelines that Caltrans is looking for. We split up the work in these 6 tasks. First was finding everything we could about those previous experimental results, how the current design provisions were developed, as well as what are the best analysis techniques. In task 2, since we're going to be evaluating a really wide range of cases, we wanted to make sure we had a good selection of what the parameters that we were going to investigate. Definitely member slenderness, definitely cross-section size, definitely boundary conditions, but not concrete strength, for instance. We would then develop and validate refined second-order analysis method, and so this is probably, I'll get to it, but it's when we say refined, it's really our best guess of true behavior, not necessarily something that the engineer would want to do. Researcher's tool, and we'd have lesser levels of refined that we're going to have guidance on for the researcher, for the practitioners. From there, we evaluate the current methods, and then develop and verify modifications to those methods. And lastly, we want to get those final guidelines and ensure the engineers can do them by confirming that they work in CSI bridge. So I'm going to step through a few of these tasks and looking at some of the highlights of the work that we've done so far. So first would be the development and validation of a second-order analysis approach, second-order inelastic analysis approach, and this is our best guess of true behavior against which we are evaluating and benchmarking current and trial design procedures. So we're using OpenCEAS with mostly off-the-shelf parts. For short-term loading, we're using the concrete stress-strain relationship by Mander et al., a very well-used and known stress-strain model, and pretty simple elastic perfectly plastic for the steel reinforcing bars. Kind of a neat thing with this project is we're evaluating long-term loading, and there is a suite of material models in OpenCEAS that deal with long-term effects, the TD concrete models developed by folks in the Midwest, Notre Dame. And for these models, really we're focusing mostly on single columns, so the structure itself is not that complicated. We've isolated it to the one member. But we wanted to validate these, even the well-used model, just to confirm that we were going to be getting good results, and so we see the comparison between 432 experimental results to our analysis model, and this is a histogram showing the ratio of the maximum load from the analysis divided by the maximum load from the experiment. There's a good bit of scatter here, but the mean is really darn close to 1, so we felt like we were getting a pretty good estimation of short-term behavior. For long-term behavior, there's fewer experiments, and it's a little harder to make those comparisons. What we have here is 8 pairs of experiments experimentally tested by some folks in Purdue. And in the bar chart, this is the difference really the reduction in strength due to long-term effects. So there was one experiment on a column tested right away, and one where the load was held for about 100 days, and that reduced the strength because it increased the deformations. So the reduction in strength is evaluated experimentally and then evaluated using the OpenSeis model that we developed, and the comparison here is showing pretty darn good results, in my opinion, for the evaluation of those long-term effects. Again, these are just the highlights of the development and validation of this model. I'm going to move on to the design method evaluation. So the approach that we took to evaluate how good, how accurate, what the unconservative and conservative errors are in the design methodology. The first step is to get our best guess of true behavior, the best guess of what these columns, each column instance we're looking at, how strong it is, what the maximum applied loads, maximum loads that we can apply to these columns. So we did that by running the second order inelastic analyses in OpenSeis, and we found the load that causes failure. We're mainly looking at the applied loads, the first order moments, the applied moments at the ends, M1 in this figure. That's because in design we're going to be running an elastic analysis, and the delta in the P delta is going to be different when you're doing an elastic analysis versus an inelastic analysis. And the better apples to apples comparison is by looking at the applied loads which cause failure versus and the two different approaches. So what we have in the graph, the solid red line, this is an interaction diagram developed with several analyses to identify the maximum permitted applied loads for a particular column in this pinned condition. Then we come up with comparable curves using the design provisions. And here the main thing to think about is the choice of the flexural stiffness to be used. There's two different equations in AASHTO, and there's a commonly used equation in ACI that's also worth looking at. So we've got our cross-section strength on the right, but really there's P delta effects, and we're going to take those out to determine what are the maximum applied loads that the design methodology says we can apply. If we have a higher EI, there's going to be less P delta effect, less moment we need to take out, higher applied loads are permitted. We've got these three different curves for the three different existing EI equations. And now I'm going to compare the maximum loads or the loads that cause failure from the OpenSeis analysis. We're going to compare those to the maximum permitted applied loads per the design methodology. And from this, we're going to be able to identify regions of conservative and unconservative error. So I'm going to highlight one region here. Notice that where the arrow is pointing, the red curve, the OpenSeis model, our best guess of true behavior, is towards the outside, and then the two different design approaches with the AASHTO EI values are towards the inside. So points in that region are applied loads that OpenSeis, our second order inelastic analysis model, is saying are okay, but the design method is saying it's not okay. So that's conservative error. This region down here is a region of unconservative error. So these are points, pairs of applied loads, axial load and bending moment, that the design method says is okay, but OpenSeis, our best guess of true behavior, is saying is not okay. It's down in that corner because it's got little axial load and a lot of bending moment, and you got a lot of cracking in that situation. That was one case of a column. We did a lot of cases of columns, specifically 3,000, with variations in cross-section shape, circular and oblong, different diameters, different steel ratios, different column lengths, sway and non-sway with different boundary conditions. The material parameters, however, were always the same at 4 KSI and 60 KSI for the concrete and the steel. Evaluate all those cases and start binning them based on the slenderness KL over R and the steel ratio. we can see maximum and minimum errors. The worst case unconservative errors, the ones in red, are going to occur for the least amount of steel, the low steel ratios, and the highest slenderness. Similarly, that's where you also get the most conservative error as well, the green. So from this, what we're going to want to do is find better EIs that reduce the errors in these plots. But that's one of the things that Caltrans was looking for. Another thing that they were looking for was better estimations of the effective length factor. So with this, with the effective length factor, Caltrans practice is basically to consider the superstructure stiffness when identifying a effective length factor, but neglect the lateral restraint of abutments. We ran some preliminary analysis, open cease analyses of bridges to determine that's pretty effective. But they were missing one thing, which was in a single column bridges like this, there's actually some torsional restraint provided by the superstructure that isn't typically accounted for. So in this situation, the lateral buckling mode would be taken with a K of 2, but it could be less. We investigated this idealized bridge, very simple version of a bridge, and parameterized this key parameter, identified this key parameter, we call it little g here, which is the torsional stiffness normalized by the flexural stiffness of the column. So the torsional stiffness of the superstructure divided by the flexural stiffness of the column. And from here, I'm going to whip through this next slide because it's got differential equations. I'm not sure how many people are going to be enjoying that, but we went with the basic equation of column buckling, identified a fixed base boundary conditions, added some more boundary conditions that are translation at the top is free. And then these are the key boundary conditions here, which is the rotation of the top of that column is restrained by the torsional stiffness of the superstructure. And there's some system effects there because really the fixity is at the abutments. And so if you have, like this, a 3-span condition, it's going to be different than a 5-span condition. So we solved this differential equation using a computer algebra system to get some nice equations. We validate it versus Mastan models. Mastan is helpful here because it has elastic buckling capabilities, a little easier than OpenCease. And we have a resulting effective length factor recommendations that vary from the cantilever case, 2, when you have no torsional stiffness, down to 1, effective length factor of 1 when you have infinite stiffness. And the variation there is important. It can depend on a few things, namely that little G factor, but also the number of spans and the in-span ratio. So those are a few of the main outcomes or main drivers of the research. We have some ongoing work, specifically further development of the effective flexural rigidity, EI. We need to make sure that we're not just finding what those errors are, but reducing them with a nice equation for EI, probably one that's going to vary with P and M, similar to the ACI equation. We're going to evaluate long-term effects with our OpenCease model that can capture those. We're going to develop tools for the practical implementation of the effective length factor I was just presenting. We're going to be looking at the results and try and validate the slenderness ratio limits in AASHTO. Really, we're going to try and answer 2 questions here. At what value of KL over R is it okay to neglect second order effects entirely? And at what value of KL over R is a refined analysis necessary? We're going to come up with some rules of thumb for preliminary design, as well as recommendations for the refined analysis. And then finally, validate all those with respect to CSI Bridge to ensure they're usable. You know, the outcomes of this work, what Caltrans is getting here is a thorough evaluation of the current design methods for slender RC bridge columns, identification and quantification of the errors due to simplifications in the design method, rigorously justified and practical recommendations to reduce error in design, and overall, we're trying to help engineers be able to make more confident and accurate decisions when designing slender reinforced concrete columns. With that, I will say thank you with this lovely picture that Sharon provided us. I love seeing slender columns. Not entirely sure of the nature of those columns up there, but they're slender columns too. All right, thank you.